Let's consider number 11 from section 1.9. So in this problem, we are trying to determine the boundary points and solve the rational inequality. And we want to give our solution using interval notation. So this inequality is it's a rational inequality, and x plus 4 is divided by this difference, x minus 6, and we want to find all x's that make that less than or equal to 0. So let's take a look at solving this. Alright, so first we find our boundary points, and we do that by setting the numerator, which is x plus 4 equal to 0, and solving. And we find out that x is negative 4. We also set our denominator, and since this inequality has the equals to in it, the boundary point that makes the numerator 0 when there's an equals to in the inequality will be in the solution set. Now, if that equals 2 wasn't there, this negative 4 would not be in the solution set. So we set our denominator equal to 0. So x minus 6 equals 0. When we solve that, we get x equal to 6. Now, because this makes the denominator 0, 6 makes the whole expression undefined. We cannot have a 0 in a denominator, because that would mean we're dividing by 0. So this is not in the solution set. Alright, so we have the boundary point. So in this box, you would put a negative 4, comma 6. Now we want to actually solve this inequality. So what we realize is that on the number line, right now we know that negative 4 is a solution and is a boundary point, so we make a solid circle at negative 4. And then 6 is a boundary point, but it's not going to be part of the solution set. So we put an open circle above that. So there's our number line. So we know that this number makes the inequality true. This number 6 makes the inequality false because it makes the expression undefined. We want to find out what all the other numbers do. So our test intervals are the intervals from negative infinity to negative 4. So we want to find out what do all the numbers to the left of negative 4 do to the inequality. We want the numbers between negative 4 and 6. Notice when we set up these test intervals, we never include the boundary points in these test intervals. And then we want all the numbers bigger than 6. So we want to find a representative in each interval. So we'll let x equal negative 5. That's a number that's smaller than negative 4. It's to the left of negative 4. In the second interval, we'll let 0 be our test number. So 0 will represent all the numbers in this interval. Negative 5 will represent all the numbers in the first interval. And let's let 7 represent all the numbers in the third interval. Alright, so our inequality is x plus 4 over x minus 6 less than or equal to 0. Alright, so we're going to replace x with negative 5, our test number. And we get negative 5 plus 4, which is negative 1, over negative 5 minus 6, which is negative 11, less than or equal to 0. So we wind up with 1 over 11 less than or equal to 0, which is false. Okay, 1 over 11 is not less than or equal to 0. Now let's try 0 as our test number. So 0 plus 4 is 4. 0 minus 6 is negative 6. And that's the same as negative 2 over 3, less than or equal to 0, and that's true. And then let's let x equal to 7. 7 plus 4 is 11. 7 minus 6 is 1. So 11 over 1 less than or equal to 0. 11 less than or equal to 0. 11 is not less than or equal to 0, so this is false. All right, so the solution set here to this inequality are all of the numbers between negative 4 and 6. And we know negative 4 is included in the solution set because negative 4 makes the inequality true. That's why we have that solid circle on the number line there. And positive 6 is not in the solution set because 6 makes the expression undefined. So that's what our solution set is, and that's how we would solve that problem. So when we go to, in this box, we would be putting this interval.